Okay, so I think as discussed in the last weeks, let's go through the definitions uh, before we solve some problems. Um, so basically, what is Markov property is uh, if chain at time n plus one, uh, if you want to evaluate the probability that xn plus 1 is x, given xn is some y and xn minus 1 is some other stage y1 and so on y2, right? Now you can discard all the information apart from the most recent one, that is xn, right? So this is the Markovian assumption, right? Everything you do is coming from this, just this assumption. Okay, so just summarizes this in one statement. Your future is independent of past given the present. Okay, um, so that's what this means, right? That's what it is, a Markov chain. So we'll go through quickly some of the important things in this, right? So one is Chapman-Kolmogorov equations for discrete time Markov chain. So this notation p to the power of n plus 1 of x comma y, it means you are in state x, and after m plus n transitions or steps, what is the probability that you are in y, right? So you can see initially you are in x, and uh, what this x m plus n, in n plus n steps you should be in y. Okay, so this doesn't mean that between 0 to m plus 1 it's not in y. It can be or it cannot be in y, but at m plus n it should be in y. That's all it means. Okay. Um, so yeah, there is a simple relationship between this and m and n step transitions is just condition on xm, okay, or xn, anything you can do, and you sum over all possible values of z, you get this thing, the above one, right? These two are equal, and this one you expand the conditional probability. So you just expand this guy, xm given x naught, and probability of xm plus 1 given y. I think yeah, that was cropped. So this is the given xm is equal to z and x naught is equal to x. Okay. But this thing is xm is z given x naught is x, but this thing is same as this thing, right? Xm plus n is equal to y given xm is equal to x. You discard x naught because of Markovian assumption, because xm is the most recent thing, right? So this thing xm plus n is equal to y given xm is equal to x is same as xn is equal to y given x naught is equal to x, because essentially what it means is at m you are in x, right? Sorry, at m you are in z, and in next n steps you are in y. So basically it's the same as x0 you are in z, and in n steps you are in y, right? So there is something called as homogeneity assumption we are doing, because your transition probabilities doesn't vary with time. Okay, so when you expand this, this is what you end up getting, p m plus n in times x to y is same as in m steps you go to z, and from there in n steps you go to y. Okay, if m plus n is equal to 10, you can decompose m and n as you wish. Okay, clear, right? Okay, Yeah, hitting times. What is a hitting time? As say ty. You define hitting time ty as the first time you are visiting the state y. That's why it is minimum of n such that xn is equal to y. So xn minus 1 cannot be y. If ty is equal to n, x naught cannot be in y, x1 cannot be in y, up to so on, xn minus 1 cannot be in y. Okay, that's the meaning of ty taking n. That's the first time you hit the state y. Okay. So what is p of x ty is equal to 2? That means this is what does it mean? In second time step you are hitting y, right? So you cannot hit y in first transition. So you can transition to something else, and then you should transition to y. So that's why p of x comma z, p of z comma y. Because you are given that you are in x, that's why you start with this, and in between you cannot be in state y. Okay, so there is a simple recursive relation. If you are given a probability transition matrix between ty is equal to m and ty is equal to m to m minus 1, right? So this is very simple. You just expand with x1 is equal to z. Okay. What does this mean? It means you are visiting y for the first time in m steps. So in first m minus 1 steps you haven't visited the y. Okay, that's why you don't put z naught equal to y here, right? And so that's it, right? So I hope this step is clear. And from this to this step, you here this is straightforward. X1 is equal to z given x0 is equal to x. And in the second step you have used a Markovian assumption and you remove x0 is equal to x from this thing, right? So what does this mean? Is you are in some state z, and in mth step you are in y, state y. So this is nothing but as good as saying at state 0 you are in z, and in m minus 1th step you are in y, right? So that's why you can write this thing like this. Okay, so this is a simple recursive relationship. This is clear? Okay, so let's revise what is transient states and recurrent states. You define a quantity rho x to y. This is a definition. Is a probability that you end up visiting y in finite time. So that's what this thing means, right? P of x of event ty is less than infinity. Okay, you eventually visit y. That's what it means. So this is just an expansion of that, right? The second line, whatever I'm highlighting, this one. And now a state y is said to be transient if this quantity rho yy is less than 1. Okay, so and recurrent if rho yy is equal to 1, right? This probability is 1 for recurrent states. Of course, this you need to replace y here with x. Okay, that's what it means for a state to be transient and recurrent. And especially intuitively you can see that transient, you will visit the state finitely many times, and this thing for recurrent states, this probability is 1, so you will visit that infinitely many times intuitively. Okay, so now let's define the quantity number of visits to y, ny, that's what I meant here. Number of visits to y is the indicator function of state y of xn, right? This is 1 only if xn is equal to y, 1, else it is 0. Okay, now what is the probability that ny is at least 1, right? So this is same as saying that you visit 1 eventually, right? So that's just this thing, this quantity. And similarly, ny greater than 2 is you visit a y at least 2 times, right? So that's why you have to say you are visiting y, px of ty is equal to m, right? So for the first time you visit y and then end up visiting y again. That's why py of ty less than. Okay, so proceeding similarly, you can generalize that number of visits to y is at least m is same as rho xy when you visit to y and then end up visiting y m minus 1 times. Okay, so yeah, so some again, right, some definitions on these things: stationary distribution and null recurrent, positive recurrent, what I mean by closed set of states, a periodicity, right? We will quickly go through all these things and then solve some problems. Okay, so you have a stationary distribution when it satisfies this equation. Okay, pi is equal to pi p. Okay, and so ty is the expected ty is the time to visit y for the first time, right? And expectation of y has a similar interpretation, that you just take that on an average, like what is it to take visit the state y. Okay, so when does a stationary distribution exists is your chain has to be a periodic, your chain has to be then irreducible, and your chain has to be positive recurrent, right? Only then you have this distribution, at least for finite set of uh, states. Okay, so once you define my, right, uh, one can show that if your stationary distribution exists, right, pi y is, you can compute as 1 over my. Okay, or my is equal to 1 over pi y, because that is simpler to compute. Okay, and null recurrent, what do you mean by state chain is null recurrent is if you have a state whose expected time to visit y, right, is infinity. Positive recurrent, that is less than infinity. So by definition you can see, right, intuitively it explains that a finite chain cannot be null recurrent, right? Because you end up visiting the states, all the states, right? Typically this will come only for infinite chains. Okay, so right, and you call a set of states, right? If S is the total number of states and C is a subset of states, you say that they are irreducible if X and Y belongs to C, right? Right. So then the row XY is non-zero. Okay. So eventually you start at any state in that C, you end up visiting the some other state in C. Okay. So that set of that kind of states, you call them as irreducible. So one can decompose the entire states of Markov chain as transient states and recurrent states, right? Again, within the recurrent states, you can decompose them as some set of classes, right? C1 is some subset of states, C2 is some subset of states, right? So what happens is eventually your Markov chain, as the time progresses, it will be eventually any one of the C1s or C2s. It won't be in ST, and within SR also it will be in any one of this C1, C2. Okay. And what is the period of a state, right? It is this thing. It's a GCD of, let's say, period is defined for a state S. It is the greatest common divisor of all those integers for which this quantity is positive. Remember, Pn of S comma S is you start from S, and in n steps you again land up in S. Okay. So if the period is 1, then you say it is aperiodic. And once you know it is irreducible, right? Typically, the irreducible, you can observe that from the chain itself, right? We'll see. I think there are some examples on that. So when the set of states are irreducible, and you know if period of any state is 1, then all states have same period. Okay. So these are theorems that I am not proving, but yeah, just take it for granted. You should be able to look up to any standard texts as well. You should be able to find. Reducible Markov chains are like disjoint graphs. Right. But initially they won't be disjoint. They are connected. Eventually, once you land in them, right, you won't leave those set of states. Yeah. So all the Markov chains are directed always. So there's something called as undirected Markov chains in probably in machine learning or probabilistic models you will learn. So they're called as Markov random fields. Right? But we are not discussing that, at least in this thing. Okay. We constrain our discussions to Markov chains, general stochastic processes, and Poisson process only. Okay, so let's define the quantity g of xy to be expected number of visits for a chain, expected number of visits to state y for a chain that is started in x, right? It is just the expectation of this quantity. Which one is this expectation of this quantity? Okay. Right, so you know that I of y is 1 when xn is y by definition. So that's why this is nothing but Pn of x comma y. N is going from 1 to infinity. Okay. G of xy is the expected number of visits for a chain that has started in y. And then further characterization of transient and recurrent states is this thing. For transient states, your number of visits to a state is finite. right? And that happens with probability 1. And your expected number of visits is given by this thing, p of x y by 1 minus p of y. You can derive this from this formula. Okay. And for recurrent, right, you will visit, if a state y is recurrent, you will visit it infinitely many times. That's what it says. And same as that, right? So you expected number of visits to that state when you start in y is infinity. So another important theorem in this regard is, if x leads to y, that is rho of xy is positive, right? And if x is recurrent and x leads to y, that means then y is also recurrent. Okay. So these theorems are useful for analyzing the chains actually. Okay, so just I think we have gone through this in the last week, but just for completing, I have put it here. Just quick review of Poisson process. Okay, so Poisson process is nothing but a counting process, right? The n of t is increasing, non-decreasing function of time. Right, so there's a parameter lambda called rate, and it is Poisson process if it satisfies this thing. Right, first is n of 0 is 0, right, and you have stationary and independent increments, and in time t, if you see n observations, its probability follows the Poisson distribution with parameter lambda times t. Lambda is the rate, lambda t is the number of arrivals in time t. Okay, independent increments just simply means that your n of t2 minus n of t1 is independent from n of t3 minus n of t2. Okay, and stationary increments, obviously by its name it implies that if n of t2 minus n of t1 has the same distribution of n of t2 plus tau minus n of t1 plus tau. Okay. Okay, so let's do some of the problems, I think, which we did not do completely in the last session. Okay, so determine that if the chain is periodic or irreducible. Okay, so you see, if you can see that all states have feedback to itself, right? That means whenever you see this, it has a period 1. Okay, so that's why it is aperiodic. And irreducible, it is irreducible because there is, wherever you are, you can end up, you can reach to other state. Right? If you are in 2, you can go to 3 and you can go to 1 back again, right? Or you can stay back in 2, or then you go to 3 and then you go to 1, right? If you are in 3, you can directly go to 1, right? And if you are in 3, you can go to 2, and you can go to 3 as well. Similarly for 1, you can reach any state to any other states. So this forms a one class, communicating class, as they say. Okay. Yeah, this is another example where you have to say the irreducibility aperiodic and if it has a stationary distribution or not. Right, you can see again, right, it is aperiodic because you can see 1, it is a loop is there, right, correctly, and period of the state 1 is 1, and also you know that it is also irreducible, as you can see, because you can communicate to any state to any other state. Okay, 1 you can go to 2, and from 1 you can go to 3 as also. From 2 also you can go to 3 and 1, From 3 also you can go to 1 and 2. Okay, it is irreducible, and you know that if it is irreducible and one state has a period, say some x, then all states have the same period. So it is aperiodic, it is irreducible, and definitely it will have a stationary distribution that you can find by writing down these equations. Pi is equal to pi p, and another constraint sigma pi is equal to 1. Okay. Clear? Reducibility through the matrix, yes, you can study reducibility through the matrix, but it is painful a bit. In some situations it is easy, but in general it is a bit painful, right? So this is the example I'll show you, right? So which states are positive recurrent? So first of all, you see that this is a finite. Once you see a finite chain, you should rule out the null recurrent states. Okay, and if it has a and also if it is it has a stationary distribution that someone says, and you should immediately conclude that all the states are positive recurrent. Okay, but that's not the case here, but yeah, I'm just saying that. So which states are positive recurrent? So you see, when you are in 1, you can go to 3, you can go to 2. Okay, from 2, let's say you end up going to 4, right? And from 4, once you go to, let's say, 3, suppose you end up going to 3, where you can, what are the possible options then you have, right? Once you enter 3, you can be in 3, you can go to 6, from 6 you can go to 3. So you cannot leave this states 3 and 5, right? So definitely there is, wherever you start, from 1, 2 or 4, you will eventually visit 3. Once you visit 3, you will never ever leave 3 and 5. Right? So 3 and 5 are positive recurrent because you visit them infinitely many times, and you end up having a stationary distribution among 3 and 5 only. So that thing you can observe from the graph, right? Rows 3 and 5 you can observe, right? Okay, so let's solve some problems. Actually, this was not intended as the first problem, but anyways. Okay, anyway, since we are discussing some of the things, right, I thought of putting this. You know what is this process? When you say process is stationary, then its distribution or density. I've written in density, but taking in distribution makes much more sense, right? When you sample your random process at some n times instance, t1 to tn, right, you get a distribution across those random variables. And when you slightly shift that sampling by a constant offset, right, even then you should have a same distribution. Then it's the process is stationary or strictly stationary. Okay, and ergodicity, it means you see homogeneity in time You can say that homogeneity in time, but that shift has to be constant for all the sampling points. Only then it will hold. Yeah. And ergodicity means this thing, right? Your time averages should be equal to an ensemble average. Okay, so for a process, say x of t, you can say what is the average of the processes, say minus t to t, 1 over 2t, you integrate over x of t, and you let t to infinity. That's your time average. And what is ensemble average? You sample that process at any point of time, then you get a random variable, you take the average of that, right? Ergodicity means that time averages should be equal to ensemble averages. So in general, nothing will imply nothing, in the sense stationary process and ergodicity doesn't imply each other. Okay, they have different properties. And here is another popular notion of Whiteson stationarity, where it means that mean of the process is constant, right? And I mean, it is independent of your sampling time, and your second order property, autocorrelation, should only depend on your difference of time samplings. It should not depend like the time instance t1 and t2. That means say 2 and 4 should be same as 6 and 8, something like that. Okay, so yeah, let's solve some problems. What was this? Yeah, so in general SK, so this is for Poisson process. All problems are there's one in Markov and 3 problems in Poisson, right? So in Poisson process, this TIs are inter-arrival times, let us say, right? And SK is summing your TIs from I is equal to 1 to k. That is, SK means it's the waiting time for the kth event to occur. Okay, that's what it means. And these TIs are the inter-arrival times. So how do we do this? We want to evaluate this probability. We are given that S3, we want S3 to happen after this time t, but you are given that in time up to 1 you have 2 events already occurred. Okay, so one trivial question is okay, anyways, we'll think about it later. So this is the picture. Okay, between 0 and 1 you have 2 time instants happen. Okay, and you see, right, your t is more than 1, because you are given that till time 1 you have two instants happened already, 2 arrivals happen, right? This is same as writing like this, right? S3 is greater than t, so third arrival should come after time t. So that's what I have written here, right? 0 to 1 you have 2, and right, and this is says as any time t, and your S3 should come after this time t. Okay, so what does this simplify to, right? This is nothing but probability that 2 arrivals are happening in 0 to 1, right? And you want 0 arrival in 1 to t. Okay, and this is nothing but the denominator is 2 arrivals happening in 0 to 1. Okay, so this arrivals within this disjoint intervals are independent. Okay, so that's why this gets cancelled with this thing. 2 arrivals in 0 to 1, 2 arrivals in 0 to 1. All you left with 0 arrival in 1 to t, that is nothing but e power minus lambda t minus 1. Well, these are all following from this definitions. Okay, clear? And yeah, this is a simple problem. A random process is defined like this: capital T plus 1 minus small t. The small t is a function of time, and capital T is a uniform random variable in 0 to 1. You want the autocovariance of the process, right? So autocovariance is nothing but this Rx of T1, T2 autocorrelation minus your means at sampling time T1 and T2, right? And Rx of T1, T2 is given by this thing, E of x of T1, x of T2, and eta of x of T1 is E of x of T1, and eta x of T2 is E of x of T2. So all you need is E of t, which is 1 by 2, E of t square, which is 1 by 3. Okay, so yeah, you can just substitute these things and you can simply solve it. I think you have all the required things. Then I think this is the only complex problem. So you assume that passengers arrive at bus station following a Poisson process with rate lambda. Okay, so the only bus departs after a deterministic time t. Okay, and W is the total waiting time of the passengers, whoever they are arriving before time t. Okay, and yeah, we want to find what is the expected waiting time of all the passengers. Okay, so just say let S1, S2, so on, Sn be the arrival times of the passengers, right, in 0 to t. Okay, and what is the waiting time if a passenger 1 has arrived at S1? What is the waiting time for the passenger is t minus S1, right? And what passenger arrived at S2 is has a waiting time t minus S2, and so on, t minus Sn. Right? Say you have k passengers arrived, then the total waiting time is t minus Si. You sum it over, I goes from 0 to 0. Okay, so now you do this expectation of W, right? And because this k here is random, we don't know what is k, right? K can be k when 10, 20, anything, any number. Right, so you just have to condition it on k and then um, average across all the possible values of k. Okay, so that's what this is a crucial step. And another crucial step is this: we want to evaluate expectation of W given N of T is equal to K. So because we are given N of T is equal to K, right, we can just take, I mean, K is no longer random here. So once we take expectation of W, it is T minus expectation of SI, right? So now how do we find this SI, expectation of SI? So here I will use some result. Okay. So given N of T is equal to K, right? I mean, this is for N of T is equal to 1. Probability that S1 is less than or equal to S, small s. Definitely small s is less than T. So what does this mean? As in time instant 0 to T, you have one event happen. Now you don't know where it is, where that event has happened, and we want to estimate that what is the probability that event has happened before S, right? So that is nothing but S by T. Okay. So in general, if N of T is K, that means K arrivals have happened, right? So their distribution, then S of 1 and S of K, S1, S2, Sk, they follow order statistic distribution of S1 to Sn, and each of this S is distributed uniformly between 0 to T. Okay. I'll try to prove this thing in the uh, next session. Okay. And then once you know that it is uniformly distributed, then expectation of SI is T by 2. Because we want till the time T. Okay, so expectation of W is K times T by 2. Because this is T by 2, this whole T minus T by 2 is T by 2, and you have K, and that will be T by 2. I think this sum should go from 1. Okay, and substitute this K T by 2 here, right? What you end up getting is T by 2 will go out, and this is K times probability of N of T is equal to K. But again, this is nothing but expectation of N of T. The expectation of N of T is lambda T, and the small t is nothing but capital T. So final answer is lambda T square by 2. Okay. So it's clear. So yeah, so this is the final thing, and gleefully some hops, some B or something, hops around a triangle. At each time step, he moves from one of the vertices to other vertices, right? So we want to find the expected time to get from vertex 1 to vertex 2. Okay, and I think there is some typo in my drawing here, the state transition matrix. I have written 2 rows same, right? It should be 1 by 2, 1 by 2, 0 here. Okay, so we want so let's define mi2 is the expected time for going from vertex I to 2, right? If I is equal to 2, it is 0 because you are already in 2. Okay, you don't want that. And yeah, so mi2 is in one step to go from I to j somewhere. Okay, that will take you one step. From there you go to 2. Okay, so this is a probability that you end up reaching j, and from j you go to 2. Okay, and just write down this thing for I1 and I3. Okay, and you will end up getting m1 2 as 2. Okay. Let me stop the recording.